Welcome back. So in the last lecture we looked at global conformal symmetries of various manifolds. That was what we did last time, global conformal transformations of a manifold M. And these form a symmetry group. They form a group. And this symmetry, this group G, we can promote it to a symmetry group of some quantum system. So a quantum system, the kinematics of which are described by some Hilbert space H. And then we have this group acting on this quantum system, or this quantum system is said to be globally conformally invariant if we have some unitary representation, U, that goes from the group to the group of unitary operators acting on the Hilbert space H. We're going to say a lot more about this whole business here of representing elements of some symmetry group as a group of unitary operators. We're going to say a lot more probably in the next lecture. And what we did in the previous lecture is before we got to this quantizing business here, finding this unitary representation, we spent some time understanding the structure of this group G here. And we came up with this classification of global conformal transformations as being compositions of translations, dilations, something else, boosts and rotations, and special conformal transformations. So that was what we did in the previous lecture. And this was all global. We always demanded that the symmetries take or are well defined or on the entire manifold M. So this was, the discussion last time was also restricted to the case where our manifold was sort of generalized Minkowski space RPQ. Now, we got some hints that D equals 2 might be very interesting already at this level of the global conformal group, but we didn't explore that. So this is the task today, is to understand D is 2 a lot better. So that's the case where P is 2. Oh goodness, does anyone remember my metric? Was it -1, +1, or was it +1s, -1s? Oh, +1s, -1, yeah. Okay. So we're going to study this case, and we're going to see that this has a lot more structure, or there's a lot more freedom, is probably the better way to say it, especially in this dimension 2 case, but also when we widen our notion of what is a symmetry transformation. That's today's goal. And this falls under the title of the local conformal transformations. That's our topic for today. What is a local conformal transformation? What indeed do they look like, especially in the dimension 2 case, and what do we learn about these transformations in various cases? So that's the goal today. Now, local conformal transformations are another way to translate what that means. What does local conformal transformation even mean? Well, I'm going to give it another synonym, infinitesimal conformal transformation. So when I say local conformal transformation, what I really mean, and what you should think from now on, is infinitesimal conformal transformation. So that some transformation of the manifold takes points of the manifold to points of the manifold, preserves angles, but we only demand these properties to first order in an infinitesimal. So I'll give you a kind of picture so you have a sense of what I'm thinking about here. Here's R2, 0 before, so we can have a nice grid. So a conformal transformation is a change of coordinates from R2 to R2 that preserves angles. So there's plenty of examples that you can look up. Well, there's the shift, there's the rotations, there's the dilations. These are all rather boring to draw down. Trying to think of one that's slightly more interesting in the special conformal transformation. So if we do a special conformal transformation, we're inverting through the circle of unit radius at the origin. Let's see if I can draw this. Oh, it's a bit tricky, isn't it? I've done this many times on a computer, but I don't fancy doing it right now. So I will just draw a dilation and a rotation to represent a global conformal transformation. Okay? So we say dilate along that axis and rotate, and then something like that. So angles should be preserved. I mean, the picture's a bit bad, but you get the idea, right? So that's what global conformal transformations look like. They're just, they're a one-to-one differentiable map between R2 and R2, which preserve angles. So our interest isn't going to be on these big ones, but actually on infinitesimal ones. So I'm going to try and render a picture of an infinitesimal infinitesimal conformal transformation. So I'll do that in the next board. Again, what does the manifold look like before? It's a grid, a regular grid. Is one way to sort of imagine the flat structure of this manifold. Stick a regular grid on it. And then you do an infinitesimal. So here there's a global one we'll call phi. And an infinitesimal one is a transformation which is the identity plus epsilon something, right? So it's identity plus epsilon something. That's what our infinitesimal conformal transformations look like. And what do they do? Well, they're just the identity, right? Plus a little bit, a little sort of nudge. So that's what we're going to do to render these things. They're going to look something like, maybe they bend these lines slightly. But always you've got to meet at right angles. That's what it means to be conformal. So it's a transformation which is nearly the identity. So if you draw your original sort of lattice of original grid or lattice that we have, superimpose it over this picture here, then although the points may have shifted under the action of this infinitesimal map, they only shift by an infinitesimal amount, right? So here's a point here, here's its corresponding image, and this amount here is something of the order of epsilon. And it's determined by this infinitesimal term here, which turns out to be a vector field. So x is nothing other than a vector field because it's the derivative of a diffeomorphism. And this vector field tells you how far to displace an original point to its new image. This vector field x depends on position. And so then we ask, what are the requirements on a vector field to be conformal, not to arbitrary order, but only to first order? So that's what we mean by an infinitesimal conformal transformation. It's a transformation which is conformal to first order in epsilon. You just drop everything of order epsilon squared and demand only that. Now, sort of naively, this is less constraining than demanding that this vector field generate a full global conformal transformation. It might be, and it is indeed the case, that only imposing conformality up to order epsilon might give you some more freedom, that there might be more x's that can qualify as conformal. This will turn out to be the case. So you might wonder, there seems to be a bit of a mismatch here. We have this global conformal group, which is presumably the exponential of some generator, and the generators are always vector fields. Why is it that we can have infinitesimally conformal transformations that don't just exponentiate up to a full global conformal transformation? Why might we have more? Well, the answer is these things can be not globally well defined and still count as conformal. So you can't exponentiate them. That's sort of the quick answer. And so this is, I think, really a key and fundamental point, right? We can, before I even get into the business of classifying these small infinitesimal conformal transformations, let's just already think ahead to what consequences this might have for quantum mechanics. When we do quantum mechanics and we want it to represent the symmetries of some group, then we want it to represent the symmetries of some group, right? So we typically have a Hilbert space and then some unitary representation of some group of symmetries. This is the groups case. Now this is super solid mathematically, right? This is just what it means. Now physicists don't tend to work globally like this. They actually tend to work infinitesimally. It's often easier to reason about things if you deal with everything to order epsilon. But then what does it mean for a system to be symmetric under a collection of infinitesimal transformations? So this is let's just call this a symmetric quantum system, or some quantum system symmetric under G. That's, if you like, a sort of working definition of what it means for a quantum system to be invariant under a group of symmetries. But what if you work instead with the generators, the Lie algebra of a group, supposing this group is indeed a Lie group? So this definition, oh, by the way, works for all groups, right? This is not restricted to Lie groups. You name a group that you like, be it a finite group, an infinite group, or a horrendously evil group. Every time you want to find a quantum system that exhibits the symmetries of that group, you're reduced to just finding unitary representations of that group. So that's how you do it. Well, we will get to projective unitary representations, but as you see, there isn't sort of a great deal more that's given by that, although some crucial points will be relevant to us. But if you're working infinitesimally, what it means for a system to be invariant doesn't even make sense if the group is finite. So to talk about infinitesimals, if I have a finite group with a finite number of elements, and I can't talk about an infinitesimal reflection. You know, the group of reflections is finite. I can't talk about sort of 1/100th of a reflection. You can sort of imagine what that might mean, but that's the group itself isn't a continuous manifold. So the only way to talk about infinitesimal transformations is you demand that the groups are manifold, and then you may as well go all the way and say it's a Lie group. So then you have to assume that G is a Lie group. And then you have some Lie algebra. It's just a bunch of vector fields. Bunch of vector fields that once you exponentiate them, you get the elements of this group. So it's called the Lie algebra, sort of factor G. And then a quantum system is symmetric under the Lie algebra if you get a representation of G. Okay, that was easy. Some pi, which maps from G to, say, bounded operators on H, but probably we're going to go very rapidly past that. Right? We're not going to talk about bounded operators on H. We'll very quickly encounter unbounded operators here. So I'll be a little bit sort of vague. Just write L for linear operators on H. Problem, of course, is when H is infinite dimensional. So again, we haven't really learned anything. This is just that we're going to do exactly the same things. Once we have some representation of the Lie group, we can also talk about like an infinitesimal transformation. And then, of course, you're probably used to the fact that once you have a representation, you can exponentiate it, right? Back again. That usually gives you, by exponentiating a generator. Yo. What's my notation L of H? This means linear operators on H. I think that's pretty standard notation. Yeah, because you know bounded operators are linear, but not all linear operators are bounded. So we need a different symbol for them. So suppose you have some element of the Lie algebra, then you're used to, let's exponentiate it and get a unitary, and then we're back in case 1, right? So what we're doing here is we're just doing case 1 but infinitesimally. But what we should recognize is that there's actually dramatically more freedom when you work infinitesimally than when you work globally. You can have Lie algebras, infinite dimensional Lie algebras, which don't exponentiate up to continuous, or don't exponentiate up nicely to a unitary representation. So as soon as we have infinite dimensions, things get very interesting indeed. Lots of possible ways that these approaches can diverge. So, so one thing that goes wrong even when you have finite dimensional Lie groups is that is no longer continuous as a function of S. That can fail to be continuous pretty quickly, right? You know, if you think about the translation operator, the generator of translations is momentum. Momentum's not bounded as an operator. So this is no longer a continuous map, this exponential here. What else can go wrong? Well, you can also have infinite dimensional Lie algebras that don't exponentiate up to a group. It's another problem, which is the one we're going to encounter in conformal field theory. And you can get every combination thereof of these problems. But the beautiful thing about working infinitesimally is you can still talk about what does it mean for a system to be symmetric under an infinitesimal collection of symmetry operations, except now wherever you used to say unitary, you say Lie algebra and you say generator, Hermitian generator. So that's the only change. And so that's the way we're going to work predominantly in this course. We're going to sort of give up on this idea of getting full unitary continuous representations of our symmetries and instead work infinitesimally, which means we need to work with representations now of Lie algebras instead of Lie groups. So this is sort of, if you have a physics training, you probably never met the first version anyway, so this shouldn't bother you. But certainly the way the emphasis in the courses I've been teaching up to now has always been on groups of symmetries, then infinitesimal representations as kind of a device to getting these groups of symmetries. But now we're going to see that we have a bit of a problem. We're not going to be able to even work globally. Because the infinitesimal conformal transformations don't even exponentiate up to a group. So we can't work globally, ever. There is no global group to work in. But that doesn't mean we can't talk about quantum systems which are locally conformally invariant. You just have to use Lie algebras from now on. Okay, then let's get to understanding local conformal transformations. So the local algebra of infinitesimal conformal transformations. Let's try and understand this thing. So remember, global conformal transformation is just a map from Z to Fz for any holomorphic F. Well, and such that its inverse is globally holomorphic. So now let's ask the question, what if F is itself an infinitesimal map? So one that's within order epsilon of doing nothing, the identity. Then we can write Z gets mapped to Z, Z prime. I'll just do it this way. Z gets mapped to Z plus epsilon n Z. Well, epsilon Z. And correspondingly, the complex conjugates get mapped to Z bars. And we need that we need that these epsilons are holomorphic. So they depend only on Z and not Z bar. That's what holomorphic means. Now, there's a convenient basis for these epsilons, and that's the one that's furnished by epsilon n of Z, which is Z to the n plus 1. Oh, I put a minus sign there. Makes no difference. And this just means, well, just take the Laurent expansion for epsilon. And you'll see that every infinitesimal holomorphic function is going to be a linear combination of, well, all z's to all powers, right? So that's a basis. So let's now find the vector field corresponding to these transformations here. So let's find the vector field corresponding to that one, say. Now I see I've forgotten an overall epsilon here. So we need these things to be infinitesimal, so I'm missing an epsilon in here. Just slightly rewrite that. So remember, if you have a diffeomorphism phi, which is z plus epsilon n z, we can always write that as exponential of some vector field, which is a tangent vector to every point in your manifold, and that's a differential operator. We can also interpret this as a differential operator. Every vector field, every tangent vector is a differential operator. And then we just wonder, what is the differential operator for this vector field here? Remember, our manifold M is just nothing other than the complex numbers. So we now wonder, what is X in the case that phi, oh, okay. When we have a diffeomorphism, which is Z goes to this, sorry, I just saw that that looked like that was the argument of some function. Now, what is this tangent vector here? Well, it's got to be holomorphic. Holomorphic means it only depends on Z and not Z bar. So we covered this in the symplectic geometry course. So then we find out that the vector field corresponding to that is none other than Zn plus 1 d dz. I think there's maybe a plus sign. Oh, no, the minus sign is still there. And correspondingly, the anti-holomorphic one, so I won't leave it as X, I'll actually translate it to the notation that people use, which is Ln. I don't want to continue to have different notations. And correspondingly, there's an anti-holomorphic generator as well, corresponding to the anti-holomorphic action. So that you can verify this. It's a nice little exercise to just take exponential of this differential operator acted on some point in the complex plane and see that you get the same answer as just doing z goes to z plus enz. Nice little exercise. So now we have a bunch of differential operators. Representing the Lie algebra of this infinite dimensional collection of infinitesimal symmetries. It's infinite dimensional because, see, this basis here is infinite dimensional, right? For every integer, we have a different infinitesimal transformation. So the group product on a Lie group is induced by the Lie bracket, or the other way around if you like. So the Lie bracket is how you take two infinitesimal generators and generate another one. Corresponds to the group commutator in a Lie group. So what we're going to do is understand what's the Lie algebra formed by these infinitesimal generators. If we do Ln, then Lm, and subtract from it Lm and then Ln, what kind of generator do we get? Do we get another one? Do we get something new? Or does it close?
Sorry?
Yep.
Question to the annotation.
Yes.
Does phi mean the new point z prime, or is it the differential?
Phi means phi is a diffeomorphism. So this is, yeah, I tried to, what if I just do this? Would that make life easier? So the diffeomorphism z goes to z plus epsilon e in z is equal to some exponential of something. Yeah, I realized as I wrote it that there were, so here's the diffeomorphism. There it is, z, or the infinitesimal conformal transformation. Z goes to z plus epsilon nz. Well, that should be the exponential of some differential operator. What is the differential operator? So I should have written it that way. You should just forget my phi. Now comes like a super important calculation. What we're going to learn is that these ln's form a basis. Well, I guess that's kind of obvious that they're going to form a basis, right? If I had done this infinitesimal transformation in another one and then subtract it, take the group commutator, then it's clear that the only thing that could come out here is something that was a power of z. Let's work out what power of z. Very fascinating answer. So if you work out the Lie algebra generated by these two generators, what you get, if you get the order right, m n is this extremely characteristic infinite set of brackets here. It's the third set of brackets. So we have a Lie algebra, it closes for all we have a bunch of vector fields whose Lie brackets close. So that's a Lie algebra. It's an infinite dimensional Lie algebra. And that's where a lot of the beauty and richness comes in this topic, in this subject, is that we're no longer dealing with a finite dimensional Lie algebra, but an infinite dimensional one. This will turn out to have reasonably profound consequences for a lot of the dynamics and kinematics of quantum systems. It's got a name, it's called the Witt algebra. And I use a notation for it. I'll denote it W or Witt. Maybe I'll just anticipating that W might become overloaded later, we'll just call it width. Width equals A direct sum A bar. So A is the stuff generated by the LNs, and A bar is the stuff generated by the L bar ends. And this direct sum makes sense because everything commutes. This is an extremely beautiful thing to look at because it's not that complicated to look at this algebra. Maybe we can understand this, and indeed we can. And in fact, life is sort of reasonably good to us. We can work out all the representations of this Lie algebra, but then we'll encounter a funny and interesting problem. In fact, I may as well leave this board up there. Groups. Maybe not. No, I don't think we'll use that. We're going to find this is the Lie algebra of an infinite dimensional group, but not the one you think it is. So there's no contradiction here is what I've been saying. Infinitesimal conformal transformations aren't globally well defined unless they happen to be the generators of a global transformation. Therefore, you can't exponentiate them, so they can't form a Lie group. This is a Lie algebra generated by those infinitesimals. It's abstractly as written, it's also the Lie algebra of perhaps a group. That'll turn out to be the case. But not that of infinitesimal conformal transformations. Okay, what else do I want to say about this? I think that might be it for local transformations. No, I wanted to just draw the connection between this Lie algebra and the Lie algebra of the global conformal transformations, because this will turn out to be highly relevant when we're doing conformal field theory. So now let's understand which of these LNs correspond to global transformations, just infinitesimal global transformations. This is an important question, right? We have this infinitesimal formulation, we have this global formulation. Which of these LNs correspond to global ones? Well, a vector field V of x is the sum of V of n Ln put a minus sign in there to make life kind of nice. So you just take an arbitrary vector field, Z obviously, arbitrary vector field, well, it's got to be expandable in terms of this basis Ln. And then we're going to ask, when does it exponentiate to a holomorphic transformation? Well, the answer is it has to be globally well defined. Sort of, there's a bare minimum you would require is that as z goes to 0, it's not singular. But that already imposes a huge constraint on these coefficients here. Namely that Vn has to be 0 for n less than equal to minus 1. Because if it wasn't, then you'd have a singularity. Wouldn't be able to exponentiate that. So it's interesting that you can have infinitesimal transformations with singularities. Sort of an interesting point, right? But there you go. So that's what it means. And now what about global means that the map's holomorphic, but also the inverse is holomorphic. Turns out, and that's an exercise, that the bare minimum is that you'd want that it's non-singular as z goes to infinity. And what does that mean? It means on the Riemann sphere. If you demand that it's holomorphic on the full complex plane without compactifying, you'll end up with just the linear transformations like last time. But if we only do things on the Riemann sphere, then we have a little bit more freedom. We can always map infinity to a finite point and vice versa. So if you work that out, a little exercise, then you learn that Vn equals 0 also for n bigger than 1 or 2. Bigger than 1. So if you have an arbitrary vector field, arbitrary infinitesimal conformal transformation, and you demand that it exponentiates up to a globally well-defined holomorphic map with global holomorphic inverse, then this Taylor series here, or this Laurent series here, is just like 0 everywhere except for 3 terms. Yeah?
These necessary conditions that you get, the lines that begin with non-singular, right?
Yes.
You get from exponentiating that and then requiring that.
So the question is, these lines where we're demanding non-singular, where does this come from? Well, it comes from being able to exponentiate it all. So if this were not true, if this were singular as z tends to 0,
Meaning? Singular meaning?
Diverges to infinity.
Okay.
So if this were singular at, say, z is 0, and you can't exponentiate that. It's a necessary condition.
Yes.
So it's a pretty weak necessary condition, right? It's, I've got on one hand this rather strict requirement that V exponentiates to a holomorphic map, And then I say, well, the very bare minimum that would require is that this generator here at least is not infinity itself. And so that gives us this requirement. But it turns out that these very weak, seemingly weak requirements here will turn out to only give us 3 generators that obey that, namely L-1, L1, L0. And then you'll see that you can exponentiate those and you find out what they correspond to. So that's the argument. Or we could have gone sort of more directly and worked out how to exponentiate these things and when this all converges, blah, blah, blah. But it would have, this much simpler necessary requirement turns out to be sufficient. So we're left with 3 generators that are allowed to apply. The rest are not allowed to be called infinitesimal generators of global transformation, global conformal transformations. Oh, and correspondingly, and these they close to form a subalgebra under the Lie bracket, which is good, right? Because you should have that 2 global conformal transformations give another one, and that an infinitesimal global conformal transformation, it better be a linear combination of some infinitesimal generators, and it better be that they close to form a subalgebra, otherwise something's wrong. So they do. You can check that they form a subalgebra. Just use those rules up there. Start substituting in your mind as you write this down. M is -1, M is 0, M is 1. And you can see already that all of it closes to form a subalgebra. So the problematic case might be M is -1, N is -1. What's going to happen there? Well, nothing. It vanishes. So that's how those weird ones get knocked out. And then the rest are straightforward. Super. Oh yeah, and which ones correspond to what? So these generate Möbius transformations, PSL2R, PSL2C. Sorry. Linear fractional. And I got sort of some very lengthy calculations which show exactly which corresponding linear fractional transformation you get for each of the 3 generators. I think I'll just write out the answer and then you can enjoy adding in the missing steps. So you might wonder which one exponentiates to what. So if you exponentiate S times L minus 1, the first generator, what you get is the transformation Z maps to Z minus S. Exercise. I only did this for real S, I might point out. Oh, and AD minus BC equals 1. Oh no, I think that works for all S. And then we come to L naught. What does L naught do? Well, we're going to do it in real and imaginary parts. So if you add L naught and L naught bar and exponentiate it, then that corresponds to the transformation e to the minus s, and that's a, for s is a real number, a dilation. So that's a translation. And then you can also work out, I think it's L naught bar minus L naught. Let's see. Okay. And then you get rotations that way. And then the final ones to worry about are the L1s, and they will give us special conformal transformations. So there you go, they're all there. All the global transformations can be found in terms of the L naughts and L naught bars. Let's just say something about matrix form. Let's label these. So we have 4 transformations there. I mean, you take the products and you get everything like looks like this. And we have a convenient matrix form sort of implied by the way I've written it there. And it turns out that composition of these maps corresponds to matrix multiplication of these maps. So there's a isomorphism between these two actions. So you can just ask, what's the matrix form of these 4 transformations here? Well, we have translations. So the matrix form of that is 1 minus S 0 1. but I could equally well have written just beta up here. Then the rotations, they have the matrix form e to the minus I, or plus I theta on 2, e to the minus I theta on 2, 0, 0. Well, that was the rotations. Well, I'm not going to write it again. That was 3. The dilations have the matrix form of lambda 0, 0, lambda inverse. And the special conformal transformations look like 1, 1, C, 0. And a final statement, which is a huge exercise, but which I ask you just to believe me, is that for the case R, D, comma naught, local equals global when D is bigger than 2. An important observation. You only get a huge set of infinitesimal conformal transformations when D is 2 or 1, really. Although you have to be a little bit sort of cautious. What on earth does conformal mean when you have one dimension? How do you preserve angles? Well, it turns out that one way to answer that question is, well, everything preserves angles as long as it's a monotone function from R to R. So the analog of the conformal group for one space-time dimension, that's 0 plus 1, 0 time, 1 space, or 1 time and 0 space, is monotone functions. So the space of all monotone increasing functions. So that's an interesting group. It's a very complicated group. And you can talk about quantum mechanics that's invariant under this group. But we won't do that here. Oh, I raised the wrong board, sorry. Now, in the last half an hour, I'm going to talk about something that doesn't get spoken about in conformal field theory textbooks, but which, to my mind, is a far more beautiful way to understand conformal symmetries in quantum mechanics. Now, you saw that there were issues to do with infinite dimensionality of the Lie algebra and the fact that infinitesimal conformal transformations don't exponentiate up to globals. Now, this is awkward and somehow not very beautiful. But let me now tell you about another case where it all works out perfectly nicely. And this is the one that's arguably more physically relevant. So you don't find this in the usual treatment of conformal field theory. In fact, I don't know any other treatment except in the book of Schottenlohe, which I recommended in the first lecture. So let's deal with a two-dimensional case, but not Euclidean space-time, but the actual physically correct one, right, which is R1, 1. And we don't live in Euclidean space-time. Euclidean space-time is fantastic and wonderful for describing statistical mechanics. That's where you've rotated time to imaginary time, corresponds to temperature now. So there's a very beautiful way to build effective theories for statistical mechanical systems, but is not directly related to physics as we know it, namely in Minkowski space. This is physics as we know it, admittedly with two spatial dimensions suppressed. So we imagine we live in a universe where we're constrained to move along a line and not allowed to explore the other two space dimensions. So this is okay, you know, this is the approximation of one-dimensional physics. As long as you have some huge restoring force, you'll be in this regime. Now the conformal group, back to groups, not infinitesimals, of R, 1, 1, special. It's very special indeed. Firstly, it is a group. So I'm going to summarize the properties of this group in the form of a theorem. So remember, what is a conformal transformation? Well, it's something that takes a manifold to itself and such that the induced metric, the pullback of the metric, is a scalar multiple of the original metric. So let's work out what those words mean in the case that the metric is 1 minus 1. So this theorem tells us a bit more. It tells us about smooth maps from a subset to R1, 1. So this map is conformal, meaning it pulls back that metric to a scalar multiple of the diagonal one, if and only if some conditions are satisfied. Oh, this means partial derivative with respect to x.
The first one always has to hold.
First one always has to hold, yeah. So you should recognize those equations. So before we go on, I'm just going to draw for you what does an arbitrary conformal transformation of Minkowski space actually look like. And that'll give you a lot more intuition, I think, for the final result. So a conformal transformation of Minkowski space must preserve the angles. That's what it means, conformal. Now, unlike Euclidean space, it turns out we've got a lot of freedom how we do that in 1 + 1 dimensions, a lot more than what you might think. Oops. And the best way to see that is to go to light cone coordinates. So if we measure locations in Minkowski space in terms of coordinates on light cones rather than the usual x and t, then we'll be able to make this really clear, this action of the conformal group on Minkowski space. So here's R1, 1. Now we could use the regular rectangle grid, but this is very terrible in Minkowski space and you should never do it because the regular rectangular grid suggests that some points are far away when they're actually exactly next to each other in the metric, right? Because along light rays, all points are a distance 0 apart from each other. So instead what we do is we measure all the locations relative to the light cone coordinates, which are these, on light rays like this. And then right angles to that, we have this regular grid here. There you go. This is Minkowski space before the transformation. Now let's wonder what kind of really not a lot of contrast there between green and purple somehow. So I'll use a different color. Use green and red. Now, what freedom have we got to change coordinates while preserving angles? Well, don't think in rectangular coordinates. Rotate your point of view 45 degrees, and then, I hope the answer will slowly become clear, any transformation which dilates in any arbitrary fashion along a light ray like this will preserve angles. Correspondingly, any transformation which squishes and deforms along this 45-degree axis will preserve angles. All angles will be preserved by that map. So I'll just give you an example. So the reds go this way. So we could bunch up the light rays here and then make them far apart here and then bunch them up here. That would be conformal, as long as we left the other coordinate axis untouched. Correspondingly, we're allowed to bunch up, dilate, and contract along the other light ray axis, and that would still be conformal. Why does this preserve angles? Well, it certainly preserves right angles. And go infinitesimally close, and you can see that it always preserves right angles like that. And then,
it just happens.
yeah, then you can, well, it's an exercise, but also what does angle mean in Minkowski space? You have to worry about space-like and time-like, but really you mean that the metric is preserved up to a scalar multiple, right? So that's the preserve angles is perhaps not the right terminology to use here. And I mean, so it's a good question, what does it mean, preserve angles? Because you're tempted to draw the cosine of an angle and blah, blah, blah. No, really what you should just think is, does it preserve the metric up to a scalar in a little region? And actually, I think this picture also makes it clear that it does, right? So all conformal transformations in Minkowski space, it turns out, have this form. They're just two completely independent operations that squish and dilate along the light cone axes. And we can capture that with a theorem. Completely characterizes the conformal group in 1+1 dimensions. So the way it works is we're going to go to light cone coordinates. That's what most of this theorem is going to be about, just translating to light cone coordinates. There we go. We've just gone to light cone coordinates. X plus y, x minus y. These are the two coordinates that label a location on a light cone grid. So for any infinitely differentiable function just of the real line, then we can build an infinitely differentiable function going from R2 to R. And what does it do? Well, it just says go to light cone coordinates and let f be defined on one light cone axis and f minus be defined on the orthogonal light cone axis. So it's just a notation so far. What this has to do with the conformal group we'll see in a second. Although I hope you can see what this has to do with the conformal group already, because this function here that squishes and dilates is none other than one of these f pluses or f minuses. This is continued, part of the theorem, continued. So now we're going to build a connection between infinitely differentiable functions on the real line and conformal transformations. So there it is, there's the connection. Given two infinitely differentiable functions, f and g, we can build ourselves a nice diffeomorphism of R1, 1 by this prescription here. And all this means is use f to squish along one light cone axis and use g to squish along the other. That's all that means there. And the reason we like this is 1/2, yeah. Well, you don't need the 1/2, but I mean, because they're infinitely differentiable functions, you can stick the 1/2 in there. But we like the 1/2 because it shows the change of coordinates, I think, nicely. So this particular map that takes pairs of infinitely differentiable functions to diffeomorphisms of this space has some nice properties. The first one is the image of phi, which is just the set of points, set of functions uv, such that ux, by, so the image of this map corresponds exactly to those functions which obey this property here. Already, like, very interesting if you look at this characterization here of a conformal transformation in Minkowski space. One of these things is conformal. If and only if the first derivatives are bigger than 0, or both less than 0. Here's a really crucial property. Phi of f and g is bijective. if and only if the individual functions f and g are bijective. Fourth, and the one that shows us this is actually more than just some recipe, but actually is a homomorphism. Pretty radical. So this is a way to construct conformal transformations of Minkowski space in terms of something a little bit simpler, right? Namely infinitely differentiable functions of the line, not of space, but of the line. I won't prove either of these two theorems, but actually it's just a matter of chasing the definitions through. There's no tricks in any of these two theorems. Just stick in the definition, take your derivatives, and you'll be done. No magic. So this is the consequence of these two theorems. Stick them together, you learn this. You learn that the group of all orientation-preserving transformations of R1, 1 is a group isomorphic to two copies of the infinitely differentiable orientation-preserving maps of R, union with two copies of the orientation reversing maps of R. Now this is a substantial win. This is a huge win in terms of understanding this group, because this group here, that's where all the difficulty is, diff plus R. You know, these cross products here, once you know how to represent one of these on a quantum system, the cross products you can deal with by taking a tensor, and we usually just drop this component. The union means union in the sense of set theory. The union thing in between. So this is a set. This is a set. Take their union.
That's again a group.
Oh, is it a group? Yes, right? Because the product of something in here with something in here lands you back in here, and vice versa. So you never get into the situation where that union is ambiguous. They're disconnected components. Now, for various reasons, just like for the Euclidean case, it's convenient to compactify, to add infinity in. Now, I could spend rather a long time talking about compactifications of Minkowski space. Construction, at least is due to Penrose, but probably before. But I won't. The construction works by doubling your space, doubling this space, doubling that space, and then identifying a subset. I won't actually really elaborate on that, but you can sort of see from this picture what it might mean. Let's just take a look at this picture and see what compactification really means. It means, well, along the light cone axis, there is a plus infinity and a minus infinity, right? But what if we say add in that infinity, call it and identify plus infinity with minus infinity? So we turn these lines into circles correspondingly here. So that's how the compactification of Minkowski space works. It doesn't really matter, it's a means to an end. And the end is that if you repeat all this argument, you see that the conformal transformations of S1, 1, so I'll just sort of repeat this text. Of S1, 1, is isomorphic to
the case m equal to S1 as 1, 1. That's what you mean.
yeah. So you compactify, you repeat the argument that we just gave, just taking account of infinity that you've added in. And you learn that the group of all orientation preserving transformations of S1, 1 is isomorphic to this group here, diff plus S1. So this is just the circle. So the group of all diffeomorphisms of the circle, cross diffeomorphisms of the circle, union where you reverse the orientation. Now, for various reasons, we define the conformal group of R1, 1 to be this, the compactified version. So there's a definition. You don't get to argue with the definition. Well, you can say it's semantically misleading, which it is in this case, but that's what we've got. The conformal group of Minkowski space is defined to be this thing here. So we've reached more or less the end now of our discussion of classical symmetries of classical spaces. This is all classical, right? This is none of this quantum. I've made reference to quantum mechanics, but so far we've just been understanding what is the group of symmetries themselves that we're going to understand quantumly, and it's this. Arguably, the group of symmetries that occupies us in relativistic physics is this group here. Let's look forward. Where are we going to go in the rest of this course? Well, the first thing we do is we just drop this. You know, orientation reversing transformations are the same as preserving. You just send x to minus x. And then we focus on this subgroup. Because once we understand how to find quantum systems invariant under this group of symmetries, then just by tensoring them once, we'll be able to deal with the other light cone axis. So that's the chiral half, so-called chiral half. And we're going to focus our energies on understanding what quantum systems are invariant under this infinite dimensional group. Turn out that's a non-trivial problem to classify. We won't be able to do it on the group level very easily, so we'll go to the infinite the Lie algebra, which will turn out to be isomorphic to the Witt algebra, which is the one that came from the Euclidean case. So we'll see that these two approaches converge at the infinitesimal level. And then we're going to focus on what kind of representations do we need to deal with, and here we'll get a bit of a surprise. So it'll turn out that unitary representations of this group, or of the infinitesimal generators, will not lead to sensible quantum theories. And the reason is they don't give Hamiltonians with the energy that's bounded from below. They'll be unstable quantum theories. So this is, I don't expect that to be an obvious statement. In fact, I'm not entirely clear that that's a proved statement in the literature, but it's certainly all the physical examples we know will correspond to unitary, projective unitary representations of this group. And that's where we'll have to spend our energies. We'll learn how those projective unitary representations, what constraints do they put on the correlation functions of your theory, and what kind of theories they correspond to at all. And we'll understand that all projective representations are classified by a number called the central charge, and then we will be able to get into the business of building conformal field theory. So that's really the outline of the course. We've got our symmetry group. Let's start representing it.
What you meant is that you need projective.
You need projective representations, otherwise you miss out on a lot of physics, yeah. All right, that's it. Thank you very much.